Last year, on the conference in Paris, I presented a paper about the fabrication of the ingots in metallic titanium VTI4 alloy with the 6 alloying elements. But we go further, and the results is in the paper which I present now. Of course, such papers have the technical direction, but in order to pay the main attention to the results, I shall mention only the most difficult moments we have overcome and the main conclusions. GSC Chepesky mechanical plant, along with intermetallic titanium VTI4 alloy, is mastering and the smelting of another high temperature, heat-resistant intermetallic ortho alloy of VIT1 grade, based on titanium 2 aluminum niobium compound. The composition of VIT1 alloy comprises 7 alloying elements, weight %. You see on the slide. Smelting of such multi-component alloy ingots is a complex metallurgical task. This alloy was also developed by VM Moscow Institute for the needs of aviation industry, the production of aircraft engines mainly, in Russia. It is noted that main advantages of these alloys are high melting temperature, low coefficient of thermal expansion, increased strength, plastic and fatigue characteristics, good heat resistance up to the temperatures of 700 degrees, and the best heat resistant properties at the temperatures of 500-600 degrees. 5 years ago, we began to develop the fabrication of intermetallic titanium alloy ingots. In the conditions of the increasing demand for such products, the company is mastering the smelting of ingots of the enlarged weight. Manufacturing of semi-finished products from ingots requires strict control on the technological parameters of hot deformation. Currently, as a rule, the triple remelted ingots of weighing about 300-450 kilograms are used for processing. With the diameter of the third vacuum arc remelting mold of 450 millimeters, the height of such ingots ranges from 330 to 530 millimeters. It is known that the head and bottom parts of an ingot are the least favorable zones under the terms of formation of a qualitative structure by homogeneity and absence of defects. Therefore, during the implementation of an order for 6 ingots of a small weight, a scheme of smelting of the enlarged ingots with a subsequent cutting them into dimensional parts of the required weight was tested. In this case, there is no more than one problem zone in one small ingot, or it is absent absolutely when cutting an ingot, for example, in 3 parts. Besides, smelting of the enlarged ingots allows to reduce metal losses on the intermediate operations and labor costs on performance of the work, and also to decrease the total time for implementation of the order. In the course of the works, 2 enlarged industrial ingots of the VIT1 alloy with a diameter 450 millimeters of triple melting scheme, you see, triple vacuum arc remelting with the estimated weight of 910 and 1480 kilograms were obtained at the GSC CMP. The following materials were used for smelting ingots: titanium sponge, zirconium, aluminum, silicon, and complex master alloys, niobium titanium of NT47 alloy, molybdenum tungsten titanium aluminum, aluminum tungsten titanium, and tantalum aluminum. The alloying elements having the largest content is in alloy are introduced. Aluminum, mainly in pure form and partly as a part of master alloys, and niobium as a part of NT47 master alloy, with a niobium content of 50-55 weight %. The main attention was paid to minimizing the oxygen content in ingots as the most harmful impurity affecting the processability of metal. The oxygen content was limited in this work by requirements of not more than 0.06 by weight. It can be performed by selecting the budding components and setting the melting parameters. For this purpose, the lots of titanium sponge with the oxygen content of not more than 0.025% and the lots of niobium titanium master alloy with the content of the sum of oxygen and nitrogen not exceeding 0.05% were chosen. These components contain the greatest amount of oxygen in comparison with other master alloys. From the parameters, it should be noted the limited actual leakage into the vacuum arc furnaces and welding units within the bounds of 2.4, 7.8 Pascal liters per second. On the basis of Burden's calculation, the briquettes of diameter 230 millimeters were pressed on a vertical hydraulic press. To obtain a strong briquettes from a large number of budding components, they were placed in a press matrix in a special way. The density of briquettes was 3.5, 3.6 grams per square centimeter, cubic centimeter, or about 66-68% of the theoretical value. The obtained briquettes were stacked in columns and longitudinal welded seams were applied to the lateral surface of the column in the electron beam unit, thus forming the consumable electrodes of the first remelting of sufficient mechanical strength. For an ingot number 1, 3 electrodes were welded with a weight of nearly 300 kilograms each, and in ingot number 2, 5 electrodes weighing from 260 to 320 kilograms each. The weight of the electrodes was increased gradually in order to estimate their mechanical strength. That was also one of the difficult moments. The melting vacuum arc furnace is shown on slide 9. The subsequent consumable electrodes of the second and third remeltings were welded with ring seams on the butted ends of ingots in vacuum units equipped with electron beam thermocathode or electron gas discharge gun. There we met one problem more: high sensitivity of the material to thermal stresses, which is expressed in the formation of surface cracks. You can see them on slide, on and around the places of locally melted metal. Some most dangerous cracks were welded in the second time. The ingots of the first war are shown on next slide. The surface crust of sublimates was deleted by turning. The numerous rough surface defects are peculiar to such ingots. The third vacuum macro melting of both ingots, I remember, was carried out in a mold with a diameter of 450 millimeters. To prevent the formation of a shrinkage cavity, the mode of stepped soaking was selected for its removal. It also was a new moment for such kind of alloys. The carried out ultrasonic control of the head parts of the ingots confirmed the absence of a shrinkage cavity. The next moment, taking into account a big diameter of ingots and their enlarged weight, the selection of cooling modes consistently in vacuum and in the environment of helium was carried out in order to prevent the formation of cracks on the top end of the adjacent lateral surface of the head parts with a sharp change of thermal load, for example, cooling or heating. The unloaded ingots had a surface with shallow blisters and tightly adhering with gaps crust lower 1-2 millimeters in thickness. From the enlarged ingots, 6 ingots were produced by cutting into dimensional parts according to the specification of the customer. This is ingot under the when cutting with a band saw. And there are the dimensional parts, small ingots. Thus, in course of the work, 13 remelts were performed instead of 19, which would be required in the case of smelting the separate ingots. The specificity of intermetallic ingots is high hardness. Therefore, turning takes much time and leads to the increased consumption of cutters in comparison with ingots of widely used titanium alloys. So it's a rather great problem for us. And we are looking for the instruments, actual instruments for this operation. The resulting roughness was 1247 microns, when the requirement is no more than 50. To determine the chemical composition of the ingots, the samples were taken after removal of an external layer of the metal in the form of chips from 3 belts of a lateral surface from the ends and of the middle of an ingot, and in the form of compact metal from an ingot ends to determine the content of oxygen and hydrogen. Table 1 shows the results of chemical analysis of the sample. Of course, there are many numbers, but the main conclusion that they indicate that the ingot corresponded to the established requirements there in the second line. At the same time, it was possible to fulfill the strict requirement for the oxygen content 0.06. That's maybe the main conclusion from this work, because it was very difficult to fulfill it, really. To assess the uniformity of the alloying elements distribution along the height of the ingots, the statistical analysis of the results was carried out using standard parameters. They are also on the slide. They are range of dispersion of the values, standard deviation, and coefficient of variation. They are given in this table. It should be noted, the main what to pay attention is the narrow intervals of variation, intervals of range, red color, of variation of actual data in comparison with those established there in the upper line. And this applies both to alloying elements with a high content niobium and aluminum. You see, niobium 38-42% and aluminum 10-12%. And also the elements with small consumption, silicon and molybdenum. The coefficient of variation, and next we shall pay attention to the coefficient of variation, which characterizes the relative measure of deviation of the measured values from the arithmetic mean, and which is a clear measure of uniformity. It is in the range of 1.7, 8.3 is ingot number 1, 8.3 and 1.7, this range, with estimated weight of 910 kilograms, ingot number 1, and in the range of 0.9, 5.3 for an ingot number 2 of larger estimated weight, 1480 kilograms. The largest values of the coefficient of variation are noted at silicon, but with a planned transition of a more accurate determination of the silicon content to a thousandth of a percent, one should expect a decrease of the coefficient of this variation. At the same time, the least value of the coefficient of variation 0.9 has niobium with the largest content in the alloy. It is important to know the high distribution uniformity of the most refractory alloying components, tungsten and tantalum. Graphically, the results of the statistical analysis are presented in figure 1, this one. The blue are the requirements, and so another colors the actual data of two ingots. You see that they're narrower. And next slide, coefficient of variation. High homogeneity of the ingot's chemical composition is confirmed by the accepted position that if the coefficient of variation is less than 10%, the variability of variation rho is considered to be insignificant. And the comparison of ingots number 1 and number 2 in terms of the uniformity of the alloying elements distribution along their height indicates that in this particular case, an ingot number 2 with the larger weight is more homogeneous. No, only these concrete ingots, because it's not a rule. So the conclusion of this work. We made two enlarged triple vacuum arc melted ingots of weight 910 kilograms and 1480 kilograms. The composition of alloy has 7 alloying elements. The chemical composition of the ingots corresponded to the established requirements and had a high uniformity. The ingots successfully passed the ultrasonic control, and from 2 enlarged ingots, 6 ingots were produced by cutting interdimensional paths. Smelting of the enlarged ingots allows to reduce metal losses in the intermediate operations and labor costs of performance of the work, and also to decrease the cycle time of fabrication of small weight ingots. And the last moment, we are interested to fabricate the ingots with different complex compositions in cooperation with other interested parties. Thank you for your attention. There, my email address. And that's all.